Hey everyone, back again with some more related rates. This time we're going to be talking about this beautiful balloon that we see here. And we're going to be solving another problem with related rates dealing with, it looks like, volume. So here's our situation. A spherical balloon is inflated at 10 cubic centimeters per second. How fast is the radius changing when d equals 1 centimeters, 2 centimeters, 4 centimeters? So again, your situation is, okay, we look at this problem. Before we have a little diagram here, we have this balloon, and we can inflate it as you're looking at it. Uh-oh, look how big it's getting. When you see something, the spherical balloon is being inflated at that 10 cubic centimeters per second, you should be thinking right away, oh, that's a rate, and that rate should be labeled as dv dt, correct. How fast is the radius changing? Okay, how fast is a rate? We're talking radius, so we're talking a dr dt. And we're looking at when d, look at d, what do you think d stands for? Diameter, maybe? So then we look at all these graphs. Look at that. Ooh, fun. What is this? Oh, look at the volume. Is it the volume? Wow. Show dv dt. This is how the volume is changing. See, why is it a straight horizontal line like that? Because the volume is not changing. It's the way the volume is changing is not changing. It's a constant. But look at dr dt. Look at how that radius is changing. I know there's a lot going on here, but you have the radius is getting larger, but how the radius is getting larger, look at that. Interesting. And I'm going to now hide all that fun stuff so we can just look right at the balloon. I'm going to stop inflating it. We're going to find when we won't want to do with d is 1. We'll say when d is 2 centimeters. Okay? Look at that. So look at that time. That's the time when it's 2 centimeters. So let's do this. Okay, so let's draw our diagram. Let's do that. So we have a diagram. We have a sphere. Oh, that's a beautiful sphere. And we have some rates. We know that dv dt, how that's changing. I think it was 10 cubic centimeters per second, was it? Yes, second. Good. We're looking for dr dt, and in this case, we're looking for dr dt when specifically 2 centimeters. When d is 2 centimeters. So you should be thinking, okay, that means when d is 2 centimeters, but there is no d that we're dealing with. We have a dr dt, but we know the diameter and the radius have a relationship. So when d is 2 centimeters, we know that r is 1 centimeter. Correct. Okay, so we're looking at that. So now you need to remember from geometry many years ago what the volume of a sphere is. But if you've forgotten, I will be more than happy to tell you. It's 4/3 pi r cubed. And a lot of times the AP exam will give you those formulas. There's some they will not give you, but I've noticed, and you'll see as you see some AP problems in class, they give you the volume ones of the sphere. So moving right along, I am going to now diagram, rates, equation, now derivatives. But before we take derivatives, let's look. First off, is there anything constant, anything that we can plug in here? No. I think if when we take a derivative, we're going to get a dv dt. That's cool. When we take a derivative of an r, we're going to get dr dt. There's no h's like in our last one, so we're going to be good to go just the way it is. So let's take the derivative. dv dt equals 4/3 pi, again, is just a number, and then we have 3r squared dr dt. Let's simplify. There you have it. dv dt equals 4 pi r squared times dr dt. We're looking for dr dt. We have dv dt, which is right here. So now we do our s and our dreads. So we have 10, 4 times pi times 1 squared dr dt. Again, this is what we're looking for, that dr dt. So this becomes 4 pi. We simply divide both sides by 4 pi, and we get our dr dt. Don't forget our units, so I'll rewrite this as dr dt equals 10 over 4 pi. And if you have a calculator, you can find the numerical approximation for that. And it's centimeters per second. So then your job will now try it when d is 1. Or when d, what was the other option here? When d was 4. and think about how is it changing. What should our answer be when we get that? What should we expect when we solve that? But there are 2 practice problems that you can do right there for homework. You watch the video, you go back and look at what we've done, look at all the notes, and see if you can't follow along and figure that out. And tomorrow in class, whoops, and we're going to cancel that. And hope you enjoyed this segment of the volume of a balloon. Johnstone, out.